I have a problem. Well, maybe problem is a bit of an overstatement. It's more like a mild inconvenience. You see, occasionally, I drill holes, and naturally, I use the drill to do so, like this one. But the problem arises when I go to actually drill the hole. I make sure the bit's in the right place, eyeball it perpendicular to the surface, and go for it. I try to keep the bit in line while I'm drilling the hole, but I don't know if it's my perspective, the fact that I can only watch one axis of tilt at a time, or just a general skill issue, where the holes usually end up just a little bit crooked. And I know there are drill presses and drill guides that could solve this issue, but those are generally bulky, expensive, and frankly a little overkill for the close enough level of precision I'm going for. So today, I'm going to make a potentially overcomplicated attachment for my drill to help me keep it level. Alright, here's the plan. For starters, I've opened up the drill and I soldered 2 wires to its battery terminals to power the electronics with. This way I won't need a separate battery for the attachment. I've got this little microcontroller, which fits nicely on top of the drill, alongside an inertial measurement unit that I'll be able to use to measure the tilt with. I also have an addressable ring LED, which will fit on the back and act as the user interface. This will show if the drill is crooked and which way to tilt it to correct for this. Now, all that's left to do is put them together. Now that the visually interesting part's out of the way, I want to talk about the code a little bit. If that doesn't interest you, go ahead and skip to the next chapter of the video. The code for this project can be broken down into 2 main parts. The first section deals with reading in the data from the IMU and determining the tilt of the drill. The MPU 6050 has 2 different types of sensors that we can use for this. With the accelerometers and some trigonometry, you can calculate the angle the drill is at relative to gravity, but this value is susceptible to a lot of noise from vibrations, like when you're drilling a hole, for example. On the other hand, if you knew what the orientation was a short time ago, you can use angular velocity readings from the gyroscope, along with the elapsed time to calculate how far it is rotated, and consequently where it is now. Neither of these are particularly accurate on their own, but if we combine them together, we get a much better estimate of the tilt. This is known as sensor fusion and is done here with a complementary filter, which takes a weighted average from the 2 values. The second section of the code takes in calculated tilt values and lights up the corresponding LEDs to indicate which direction to move the drill. During the build, I added some 3D printed parts, including this mount for the circuit board and a diffuser for the LED. I also added this power switch so it could be turned on and off independently from the drill. As you can see, the level is pretty responsive and gives a color-coded direction indicator to show you how to level the drill. The direction of the light shows which way to move the back of the drill, and the color indicates how close you are, with red being far away and green being close. Once you're within a programmed close enough tolerance band, the entire ring lights up green to indicate you can start drilling. The level also has a wall feature that it automatically switches to when the drill is oriented horizontally. In this mode, it can only correct for the up and down tilt since it has no way of determining perpendicularity from left to right. This mode can also be used to verify that any horizontal surfaces you're going to drill into are level, since this whole attachment only really works if they are.